Okay, so now we're going to look at rules of inference. In last week's tutorial, there were some informal arguments based on logical equivalences and things like that that you were supposed to work out, and that was great. But in some sense, the an important tool that probably is going to help you a lot in making those arguments is rules of inference. So let me be a little bit more careful. Let's go through this. Let's say, let's give ourselves some context. Okay, so let's say that you have two people. One of them is claiming something to be true. Okay. So this person has a claim. What is a claim? Claim is basically a statement that the prover believes is true. So this person is the prover, and the prover is trying to convince the other person. Let's call this person the verifier. Okay, and sometimes it's nice to give people actual names. Let's call this person, let's say, Alice, and this person Bob. Okay. And I didn't create these names out of thin air. Alice and Bob are a common moniker given to people in many contexts in computer science, especially in cryptography when we are talking about two people trying to communicate with each other. Okay, so Alice wants to prove something. She's claiming something, a statement to be proved. Okay. And now Bob is skeptical. Bob doesn't believe Alice just because Alice says it. Bob wants to know for sure what Alice is saying is true or not. So what should Alice do? Alice needs to give a proof. Okay, so a proof is a way by which Alice can establish the truth of a proposition. Establish the truth of a proposition. So Alice's job is to somehow give a proof to Bob, and so that Bob will be able to, it will be satisfied that the claim is in fact correct, is true. Okay. So how does she do that? How does Alice provide a proof? This depends on the context. If Alice and Bob are lawyers fighting something out in the court, they usually give a lot of evidence. In a lot of science, what you do is you run experiments to establish truth. Okay. But in the laws of logic, in the world of logic, what we do is we argue. Okay. We come up with what is called a valid argument. Okay. Let me break that down for you. What is an argument? An argument is basically just a sequence of statements. Okay. It's a sequence of statements, and the last statement is special. The last statement is called the conclusion. Okay. The conclusion, by the way, is the same as the claim. Without the proof, the statement is just a claim. With a proper proof, it becomes the conclusion. Sometimes it's called, in the context of mathematics, it will be called a theorem. Once you know that there is a valid proof or a valid argument. So an argument itself is basically a sequence of logical statements. Okay, so basically a sequence of logical statements. But these statements Just as any sequence of logical statements are not going to be good enough. Okay, there must be something more than just an argument. It has to be a valid argument. Okay? What is a valid argument? For a valid argument, you need to be careful. So there is, we need to also give a name for these statements that are not part of the conclusion. These are called the premise or premises, because there are multiple statements. These are called the premises. And now the question is, when is an argument valid? An argument is valid. So an argument is valid if the following is true. Like let's say this is premise P1, P2, P3, and so on, Pn. If P1 and P2 and so on to Pn. So if all the premises are true, then let's call this conclusion as Q. Then Q. And this has to be a tautology. Okay. If this implication is a tautology, what is this implication? The implication is, if P1 is true, if all the premises are true, P1, P2, and so on up to Pn, if all the premises are true, then the conclusion Q is true. Now, that's just an implication. If that implication is true, okay, if that implication is established, then what you have is a valid argument. Okay. If you're able to, so basically, what is a valid argument? It's a sequence of logical statements, one after another. Basically, it's a sequence of premises followed by a last one, which is a special statement called the conclusion. Okay. And such an argument is valid if all the premise statements are true, then it must follow that the conclusion is also true. Okay. If that implication is always if that implication always holds, then the argument is valid, right? So let's actually give ourselves a quick example. The most classic argument that you can think of is the following. P is some statement. P implies Q is a statement. Now, what can you conclude? Anybody? Let's give ourselves an example, maybe. P is, say, today is sunny. Q is if today, so basically, P is a statement, today is sunny. There's an implication. If today is sunny, then I will sweat. What can I conclude in this case? Anybody? Oh, it's not loud enough. So can you repeat that?
Q will be conclusion.
Q is the conclusion, exactly. Q is the conclusion. And what is Q? Q is that I will sweat. Okay. This is the most classic argument that you can think of. This is the type of argument that has been made for over 2,000 years, dating back to Aristotle and others. Okay. This has a Latin name for it. This is called modus ponens, or the more English term for it is a direct inference. Um, if you have a member, so let's connect this back to this whole idea of what is a valid argument. So what you have is a sequence of statements. You have statement 1, statement 2, and statement 3. The last statement is a special statement. It's a conclusion. So here I use this sort of therefore symbol to indicate that that's the concluding last statement. So this is what we've done is we've established that it's an argument. Now, how do we establish that it's a valid argument? How is it valid? Why is it valid? Because of this. Now, if you know that if P and you know that P implies Q, then what can you say? This when you have these two to be true, then you can conclude that Q is true. And this is always going to be this is always going to be a true statement. Okay? This is a tautology. Okay? And then what does that mean? It means that this is a valid argument. This is a valid argument. Okay? So what we have is some simple valid arguments that get repeated over and over again, and these are called rules of inference. These rules of inference basically are, little, simple, typically 1 or 2 step arguments, valid arguments, that once you have sort of digested them and understood them, then you can use them to create larger, more complicated arguments. So they're kind of like primitive arguments, so the simplest arguments, okay? Simplest and most essential arguments. Everything else you can essentially derive using these rules of inference. We've already seen one rule of inference, that is modus ponens. Let's look at some more. You please let me know what you think of should be the conclusion with each one of these. What should the conclusion be here?
Negation. Not P.
Negation of P, yeah. Okay. So what we have is first negation of Q, statement 1, and then implication P implies Q. Okay. But because if remember, P implies Q is equivalent to negation of Q implies negation of P. That's the contrapositive, right? So then you can apply modus ponens to conclude that it's negation of P. So if you were to just, this is you can basically is equivalent to negation of Q implies negation of P. So by modus ponens of these two statements, you get this conclusion. Okay? But you don't have to go through the contrapositive and then apply modus ponens. This itself has a name. It is modus tollens. Okay. Let's give ourselves an example. Let's say P is I remember the umbrella. Okay. Q is it does not rain. Negation of Q is what it, let's say negation of Q is true. Basically, what it means is it rains, and I have the implication P implies Q. This is often the feeling, right? If I remember the umbrella, it does not rain. Okay? And it's and since Q is negated, what can you conclude? Therefore, negation of P. I do not remember the umbrella. We have several more like that. Some very obvious ones.
Sir,
Yes, please.
what is the exact meaning of modus tollens? It means like whenever we have to use contrapositive, it will be under modus tollens, right?
Yeah, basically exactly this. Exactly the blue thing that I have over here.
Okay.
Exactly this. It's and by the way, these are very precise notions of arguments. You have two premises. The statements 1 and 2 are the premises. If 1 and 2 are true, then the conclusion holds, right? What is the first statement? Negation of Q. Okay, you have some proposition Q, and that Q is false. So negation of Q is true, and you know that P implies Q. Then the conclusion is negation. That's modus tollens.
Sir, I had a doubt.
Yes, please.
Sir, writing negation Q like the statement 1, it means that negation Q is true.
That's correct.
And P implies Q we are writing, that implies that P implies Q is true.
That's right.
So we have to answer the conclusion should also be true. So it
That's
is
correct.
negation P.
That's
Okay.
right. That's right. Yes. Remember, when you, for an argument to be valid, what do you need? You need negation of Q to be true, and P implies Q. This implication, if this is true, if these two are true, then then negation of P. If this whole thing must always be true. This whole thing must be a tautology. Only then it's a valid argument. And what you said just now is exactly that. You paraphrased it in English, but formally this is what it means.
Okay, sir.
Sir,
Yes, please.
sir, does the conclusion need to be unique for an argument?
No. If you have a bunch of premises, it can lead to multiple different conclusions.
Okay, sir.
Yeah. But usually you isolate them as separate arguments so that there is a clear conclusion for each argument. So, for example, P and Q. The conclusion can be either P. This can be one argument. P and Q. The conclusion can be Q. This can be another argument. Okay, these are two different conclusions that you can arrive at, but you normally state them separately so that the focus, because remember the story is Alice has one clear statement that she wants to prove to Bob, and so she comes up with a valid argument and presents that to Bob. Bob is able to look at the premises, apply the rules of inference, and decide whether the conclusion is true or not. Okay, so this is the kind of backstory that you should keep in mind, right? And for a situation like that, it's kind of nice to have one clear conclusion. But you're right that the same premises can lead to multiple conclusions.
That means argument comes from the conclusion, like based on the conclusion.
Yes. Yeah.
Okay, sir.
Because Alice wants to prove something. That conclusion, remember, conclusion starts its life off as a claim. And then once there is a valid argument and there is the truth of the claim is established, it becomes a conclusion.
Okay, sir. Got it. Thank you, sir.
So now here's what can you say is the conclusion here?
P implies R.
Yes, exactly. Okay, this is some notion of what we usually call transitivity, but in the context of logic, this is called hypothetical syllogism. This, by the way, these two are called simplifications. Okay. There's a table in the textbook with all of them, so I won't be going through all of them. I just want to go through maybe one more of them. Since I talked about this one, P or Q, and let's say you also have negation of P. What's the conclusion here?
Q's.
That's right, Q. Either P or Q is true, and you know that P is not true. Therefore, what must be true? Q must be true. This is disjunctive syllogism.
Sir,
Yes, please.
these names should we be remembering or are they just for an idea?
It will be good to remember that. It's normally I do not require you to remember these things, but these are kind of fundamental. These come up, these logical equivalences and rules of inference, they come up, and sometimes it's nice to know the precise basis on which you're doing. These are obvious. I mean, I do understand that these are also obvious, but keep in mind that you are the idea of logic is based on. I mean, it's not just. It's not just for you to understand the truth, it's also to convey the truth. Right? It's because Alice wants to convey to Bob that her claim is in fact true. Right? What that means is sometimes you need to have a common language. Sometimes you want to point out that this is exactly the reason why I believe the statement is true. Okay? And if you're able to state the precise name for that for that inference, it's helpful. Okay, and so it's not a bad idea to remember this. This is not much. This is a few things that I mean. Honestly, there are so many times that I do not want. I usually what I do is I either allow you to come to an exam with a cheat sheet where you can write some things that you don't need to, you don't want to memorize. Because it's not about memory, it's not about memorizing unnecessary details. But these are kind of fundamental, so it's nice to remember them. Okay, so I would say, I mean, it's just a good idea to remember. Now, am I going to be asking specific questions and basing them on your memory? Maybe for a very small amount, I may ask you to remember, do that, but that's not going to be the emphasis of the exams. Okay? But still, for your, I mean, but keep in mind, I'm not saying I will not ask them. It's just that will never be the emphasis. Like the primary, most marks won't be based on remembering names. Okay, but it's still kind of a good thing to remember these things. Okay? These are fundamental. I hope that addressed your question. All right, so now let me see if I can give one more. P or Q, negation of P or R. Therefore, what can I conclude over here?
Negation Q implies R.
Negation Q implies R. And actually, there's an easier way to state the same thing. I will state the same thing. I'll just state it a bit differently. Q
or R.
Exactly. Exactly. Same thing, but Q or R is the more easy thing to remember. Okay. This is called resolution. All right. So enough of these rules of inference for now. Let's actually work out a quick example. So what I'm going to do is give you an argument, and I want to establish that is indeed valid. Okay. If today is sunny, I drink Coke or drink Pepsi. If the corner shop is closed, maybe that's the only place where I get Pepsi, I will not drink Pepsi. Today is sunny and the corner shop is closed. Therefore, I drink Coke. Now let's eyeball this. The thing is this: like this is an English argument. It's still an argument. We need to establish that it is valid. What would be nice is to be able to give names for the propositions in this argument so that we can apply the rules of inference more easily. So let's do that. Let's say this, let's call this T. Drink Coke is C. Drink Pepsi is, let's say, P. Then corner shop is closed. S. I will not drink Pepsi is just a negation of P. Today is sunny, that's E. I think all the propositions have names now. Okay, is everybody clear with the names? So let me just make this a little bit smaller so that we will rewrite this whole thing in notational form. Okay. What is the first statement? T implies if today is rainy, is sunny, I drink Coke or Pepsi. Then what can I say? I C or P. If the corner shop is closed, I gave the name S for it. Then the conclusion is negation of P. Okay, I will not drink Pepsi because only that corner shop sells Pepsi. Now today is sunny and the corner shop is closed. T and S. Therefore, I drink Coke. Therefore, This is the argument. And sometimes when you actually generalize an argument, see, this is the argument here is very specific. Every statement has exactly one meaning. Okay? Now, when you generalize it and give variable names to these propositions, then it can be applied in various contexts, right? So sometimes when you do that, they call it an argument form. Okay? And then it's more generally applicable to any argument that fits this form. So now we have this argument form. Let's establish, how do you establish that it is true? Now, so let's try to do that. Let's give numbers for these. 1, 2, and 3. What can what does 3 imply? From 3, I get 2 more statements. Okay, I'll give them numbers 4 and 5. What are 4 and 5? Well, they're basically just simplifications of 3. So if T and S are both true, then T must be true and S must be true. These are both simplifications. Okay. And now let's see. So now if you look at this, I can use 4 and 1. What can I get from 4 and 1? 4 is the T. 4 is T, and 1 is T implies C or P. Okay. So from these two, what I can conclude is that, and I'm going to call that statement number, statement number 6. What is that statement? C or P. And what was the rule I applied? Anybody? What was the rule I applied?
Modest Collins.
Modest Collins. Yeah, exactly. All right. And now, remember, it's sometimes good to keep in mind what your goal is. The goal is to arrive at C. How can I arrive at C? If I can make a statement of this form. If I can make a statement of this form, then what I can do is I can use okay, C or P, but negation of P. So then I can use the disjunctive syllogism to conclude C. Okay. So the question is, how do I arrive at negation of P? Now tell me, how would I arrive at the negation of P? Which
2 and 5.
4 and 5. No, I will
2 and 5.
2 and 5. Okay. This is my 7th statement, negation of P. That's again, what is the rule that I applied? Again, modus ponens. And statement number 8 is the conclusion. All right. So this basically establishes the validity of this argument. So this argument is in fact valid.
So could you re-explain this solution?
Oh, sure. Remember, what is the question? The question gives you has given you an argument, and you need to establish that that argument is in fact valid. Okay. Basically, what you need to establish is that given all the premise statements, you have been able to infer new statements such that it implies that the conclusion must be true. Given the premise to be true, the conclusion must be true. Okay. So these are your 1, 2, and 3 are your premise statements.
So with the help of our premise statements, which are true, we have to prove that the conclusion is true.
That is correct. Yes.
Okay.
Yeah. So given that 1, 2, and 3 are true, we use them to infer other further statements, and then we conclude with the conclusion.
Okay, sir, understood.
No. Any other questions? Good. So that's rules of inference. When in what we've seen so far is rules of inference in the context of propositions. You can extend rules of inference to hold in the context where the statements are quantified in predicate logic as well. So we have a set of rules there as well. So I'll quickly go through them. Okay. Again, these rules of inference are going to be very, very straightforward. So we'll give them precise names to refer to them, but they're very, very straightforward. For all x, p of x, if that's a statement, then what can you conclude? You can conclude that p of c is true for any seat, or rather arbitrary seat. So when you this is what is called universal instantiation. Okay, the term may sound very complicated, but it's actually very simple. What it means is this: there is a universal statement for all x, something is true, and x can take any value, which means that when you instantiate it, when you instantiate x to a specific value, then also it's going to be true. Okay. For all rational numbers, they can be written as the ratio or the fraction between two integers. They can be written of the form a divided by b for two integers a and b. This is true for all rational numbers, which means that if you have a rational number 8.342, that 8.342 can be written as the fraction a over b for two integers a. Okay, that's what this means. It's basically taking a very broad, sweeping statement and then applying it to a very specific example. Okay, that's universal instantiation. And we have a if there is instantiation is going from broad, general to narrow, specific. Okay? The flip side also can hold. You can go from specific to broad, but you need to be a little bit careful. Suppose P of C is for arbitrary C. So basically, what I mean by P of C for arbitrary C, that means I've established the truth of the statement P of C using only the fact that C is in the domain. Okay? So I'm not, that's essentially what I mean. And in the obvious thing here, the obvious conclusion is that for all x, p of x. This is called universal generalization. Generalization. And how does this play out in proofs? What we'll do is we will try to say, look, we're going to talk about rational numbers. Let's fix a rational number r. Now r is a rational number, so it can be written as a divided by b, and then you make an argument, and this entire argument holds as long as r is a rational number, right? But our focus was on that specific rational number r. Then we can generalize. So look, we are not using the fact. I mean, we are simply basing the argument on the fact that r was some rational number, and so the conclusion. This it can be generalized to all rational numbers, and that's exactly what this says: universal generalization. Okay. Let me a couple more. We're almost done. I know it's getting late for you guys. If there are universal instantiation and universal generalization, let's see what we can find for existential stuff. This is existential instantiation. But we need to be a little bit careful with the subtlety here. When we did universal instantiation, we were able to say something a little bit more general for any arbitrary c. Now, when you say there exists x, p of x, then the conclusion can be p of c for some element c. It doesn't hold for all c. It holds for some element c. Okay. What we can the way this will get applied is as follows. If you let's say you have a statement that there exists a rational number such that some property holds. Okay. Then what you can do is you can pick such a rational number and then continue the argument for those things. Okay. If you don't have there exists a rational number with a particular property, then you're not guaranteed to be able to pick such a rational number. This is what allows you to pick such a rational number. So if you can prove that there exists a rational number with a particular property, then you can pick such a number and continue the argument. And so for all of those things, you use basically existential instantiation. And last one, if there's existential instantiation, there must also be existential generalization. P of c for some element c. Or if you show that the property holds to some element c, then you can make a general statement that says there exists an x such that p of x. Okay. This is the generalization statement. Any questions? Let's see if I can. I just want to take a minute to maybe see if there's one example perhaps that I can work out. Actually, let me see if I can.
Sir,
Yes.
sir,
I didn't understand the difference between last and the last but one example.
Oh, the instance, the existential
Generalization
instantiation.
instance.
Okay, yeah. Give me a second. Let me. I wanted to see if I can do something. Thought I could do this. Okay, let me not do that now. I don't think we'll have time for that. I'll work out examples later. Let's look at them carefully. Okay, this is the existential instantiation inference. What is the premise? There exists an X such that some property holds. So let's give ourselves an example. There exists an even prime number. Okay. Basically, the domain is prime numbers. Okay, the domain is prime numbers, and in that domain there exists an even number. If you establish that, then the conclusion is that the even so maybe yeah. So the p of x here, this is p of x is prime. Sorry, x is even. X is even. So the letter is a little bit confusing, but let me stick to that. Okay. So let me make okay an even number in the domain. Okay, the statement p of x is that x is even. This statement, there exists x p of x, is the statement there exists an even number in the domain. And what is the domain? Domain is the set of prime numbers. What can we conclude? What we can do is, therefore, the statement p of c is true for some element c, and in this particular case, the element is c equals 2. So basically, you can pick a prime number that happens to be even. That's all there is to it. This is a very simple statement. It's just a it may seem complicated, but it's actually very simple. All it's saying is that if you have a statement like this, there exists some x that satisfies some property. You can pick such an x that has that property. So here there exists an even number in the domain. That's the another way of stating it is there exists a number in the domain that is even. Okay, which means that you can pick such an even number. And what is that number? The number is 2. You can pick that and do some further manipulation or argument based on that. Okay. Is that clear?
Yes.
Okay. And I hope now that this will be clear. Basically, this is the opposite, existential generalization. If you can prove that 2 is a prime number and 2 is an even number, then basically, if you can prove that 2 is an even number, and it happens to be the domain of prime numbers, then what is the conclusion? You know that there exists an even prime number. This is a generalized way of stating it. That's all. And that's called existential generalization.
Yes, sir.
Maybe think of another example just to be for example, if you can find, let's say, Mr. XYZ is an honest politician. If you can give me one such honest politician, and this is a specific person, I'm not going to give a name here because I'm not sure I have an answer to that. But let's say you are able to give me such a politician, then what can we say is that there exists X such that politician X is honest politician. Okay. So to basically, if Alice wanted to prove that, what she needs to do is just find one Mr. X who happens to be an honest politician, and her job is done. That's essentially what this means. Okay. Any other questions? Okay, we are out of time now, so let's stop here. Tomorrow, what time is our class? I have to keep reminding myself. Tomorrow, our class is from 4 to 4:50. So I will see you guys tomorrow at 4 o'clock.
Sir,
Give me a second, let me stop the recording. Yeah, now the class is over, so you can leave if you don't have